Welcome everyone to the 7th session of the Connect University Autumn School on Secure and Sustainable Digital Infrastructures. I'm Alex and I will be your host for the entire week. And today, merely warming everyone up for our main topic, high performance computing and quantum infrastructure deployment in the EU. Now, we started back in 2015 with Connect University, and we are the knowledge sharing flagship of DigiConnect of the Commission. And we aim to update both the EU staff and you, the general public, about the latest digital trends, as well as important digital policies. The scope of our sessions in general is to put at the same table EU institutions with industry, academia, and international organizations, helping us find inspiration from each other, but also identify current opportunities and threats to digital policymaking. For those of you who are not yet connected on sly.do, we invite you to do so using the code HPC. I say this because over there you can ask questions and we will make sure that they make their way towards the speakers of today. Also, in case you have any insights that you want to share on social media, we encourage you to use the hashtag ConnectUniversity and digital infrastructures. The recordings of all the sessions will be available as of next week. But in the meanwhile, you can always check the Digital EU channel on YouTube, where they will be posted, as well as the dedicated page on Futurium. Futurium, we invite everyone to join. It's the place where we can have conversations and discussions on all digital topics. We have communities for everything that you might think you might see relevant in the digital area. And there is the place where we gather sometimes inspiration for future sessions or inspiration for future developments in general in the digital area. Speaking of which, generally speaking, technology moves pretty fast, so we must run alongside with it, making sure we have the best tools available to make it in good shape at the destination. And in terms of future destinations, before we start our core session of the day, I want to simply give you a small overview of what's left of the autumn school week. After lunch at 2, we will begin with the session on industrial platforms meant to spur innovation in the economy. And finally, on Friday, we will end with the session on mobile generations from 1G to 5G, and with the closing session, which is meant to give a more holistic view of the week, see what learnings we can take for the future, and also gain some insights of the EU Commission's plan in terms of greening digital infrastructures. So we invite everyone to participate in those sessions as well. As for our session of today on HPC and quantum, in order to give a more comprehensive context, as well as shed some light for non-experts such as I, as well as for those of you which are more fluent in the matter, we have with us today Oscar Diaz, Head of Sector in DigiConnect on Quantum Technologies, Juan Pellegrin, Head of Sector in DigiConnect on High Performance Computing, Valentin Plugaro from LuxProvide, giving an oversight on Meluxina Supercomputer, Pekka Manninen, giving us an overview on Pre-exascale real case LUMI Supercomputer, and last but not least is Christel Michelsen from HPC QS. So without further ado, Juan, please, the floor is yours.
So good morning to everybody. It's my pleasure to be here today in the in this session. I just want to confirm that everything is okay. So, not this one, sorry. This is the high performance computing, and this is what we're doing here in the EU. So just very briefly, what we're doing is the use, what is HPC for newcomers, is the use of extremely powerful computers for applications across all branches of science, industry, and even public administration in the area of modeling and simulation. So you can name any discipline that can be modeled and simulated by a supercomputer. So we are proud to say that now we're entering the exascale dimension. The first exascale computer was launched some months ago. This is the aim now of the EU to achieve exascale in the forthcoming future. What are we doing here in the EU? So this is basically led by the HPC JU, which is a joint undertaking that's in charge of developing and implementing all the European HPC strategy. And this spans from infrastructure, that will be the core topic of today, where we have two distinguished speakers that will explain and develop the activities on Petascale computer, and then to the next stage, which is the Pre-exascale from Pekka from in LUMI. So I'm honored to say, although Pekka will develop further, that LUMI now is the third most fastest and most powerful computer in the world, and also is the greenest. So it's not just a question of being very powerful, but also the energy efficiency issue is also a key element for our activities. So what do we do? It's not just, as I said, not only infrastructure. We're also trying to develop in-house in Europe technology that will focus and try to become sovereign, so that we do not rely only on non-European suppliers, in particular in the processor side. So NVIDIA, AMD, and Intel are the leaders here. So we're trying to develop further technologies in this area so that we become sovereign. So the COVID-19 pandemic showed that we should not rely too heavily on external sources, because then we are a bit caught in a difficult situation. In addition, Europe is very strong in the area of applications, so we are developing applications across all different fields of science. So basically, what we're trying to do is to prepare the applications for the new systems. So we're trying to really fine-tune so that they are optimized for the new systems, so it becomes easier for users to use the supercomputers. Since there are many disciplines in HPC, and we want them to be federated, meaning that when there are jobs that need to be run in different computers, these are federated, so we are synchronized, and all the supercomputers can be optimized with services and federated. So this means that one job can be running one system, then there's a backlog, and then we can optimize the use of the supercomputers. And finally, there's no point in having great supercomputers unless these are going to be used. So we're really focusing very heavily on trying to facilitate the uptake of these supercomputers through education and skills. This includes centers of competence, so each country has a center of competence on HPC. We have launched a master's degree on HPC. We're doing a lot of networking activities, and in the short term, we're going to be the user forum. So this is in a nutshell what we're doing in HPC in the EU. This is very much led by the EU, and the next dimension is going to be the exascale supercomputer. So this means, as you can say, 10 to the power 15 floating operations per second. So this is the new challenge. So Europe is beginning to regain momentum in this discipline, and this will be hosted in Germany. So we're looking forward to that. So it will be in Jülich in Germany, and now all the activities of the administration has begun, so that we can start with the process of procuring the system. So without much further ado, this is in a nutshell what we do in HPC, and then I will leave all the details for the two distinguished speakers that will present very heavily and in greater detail what their systems are doing. So looking forward for the Q&A later on. So thank you very much, and then I'll pass on the floor to to Oscar. Thank you.
Thank you. Thank you, Juan. I don't know if you can see my screen.
Yes.
Okay, thank you. So good morning, everyone. My name is Oscar Diaz, and I am the head of quantum technologies at the European Commission. We are, both Juan and myself, we are in the same unit, that is high performance computing and quantum technologies. And we are, by the way, we are based in Luxembourg. I will provide a brief introduction about the deployment of the quantum computing infrastructure, and Christel, that is the speaker, that she will define a little bit more in detail what we are doing with one of these projects. So I would like to start providing some context. Basically, in 1999, the EU was the first region in the world that to launch a public research program in quantum technologies. And later in 2016, approximately 4,000 of the researchers, of European researchers, endorses what we call the Quantum Manifesto. The Quantum Manifesto basically was defining a common strategy for Europe on quantum. And this enabled the creation of the Quantum Flagship. That is a 10-year initiative. The Quantum Flagship started in 2018, and it's a 10-year initiative with a budget approximately of €1 billion. So the aim of the flagship is not only to support research in quantum, that it has been doing, we have been doing this since the beginning, but also it's to transform the results of this research into industrial exploitation and of course, real-life applications. So the flagship, as I said, is a long-term project. But we have, even if it's a 10 years project, we already have currently finished the first step of the flagship, and we have already excellent results. In fact, the more successful quantum computing platforms started as a project of the quantum flagship, and now they are available in the market. This has permitted also to launch, as part of another program that is called Digital Euro Program, different initiatives that will permit the deployment of quantum infrastructure in Europe. So European researchers can use this infrastructure. An example of this infrastructure is EuroQCI, and another example is the quantum computing infrastructure. So as I said, one of these initiatives is focusing on the deployment of quantum computers and simulators in Europe, and this we are doing it together with the Euro HPC. The Euro HPC, as Juan said, is the one that is responsible of doing the deployment of the supercomputers. So they will also do the deployment of these quantum computers, and they will be working together, these quantum computers, with the supercomputers. This will involve, as I said, the deployment of a standalone and HPC integrated, both standalone and HPC integrated quantum computers and also simulators. The speakers today will provide a little bit more details about one of the first projects in this initiative for the deployment of 2 quantum simulators in HPC centers, in this case in Germany and France. But very soon, approximately probably next week or in 2 weeks, we will announce the result of the selection of at least another 3 hosting entities that will deploy quantum computers based on different European technologies. The domain of quantum computing is still emerging. As you know, we are still in the first stages, and it is not yet very clear what kind of technology will be best for building efficient and functional quantum computers. So therefore, it's the quantum computers we will base at this stage. We are basing on several different promises technologies that all of them has been developed in the EU and will be available to basically to researchers and industry anywhere in the EU. The idea is that this will help the users to mature these technologies further, plan also for new markets, and attract further investment for these technologies, and accelerate also the development of quantum computing applications that will solve real world problems. And just to finish, so because as I said, this is an introduction, I will like to, and today the main topic also is sustainability. I just wanted to mention 2 areas where quantum computing could play a key role. So one is the efficiency of the systems in terms of energy utilization. So we know that quantum computing will not replace classical systems, but quantum computing will improve dramatically the performance on certain use cases where classical computing is currently used. And especially now that HPC, as Juan said, is moving into the exascale area, this means that these HPC supercomputers, the utilization of power is starting to be very, very big. We're talking about more than 20 megawatts to power one supercomputer. And quantum computers here, they could help to reduce drastically the energy consumption, while at the same time increasing the performance. We're talking in some cases up to 1,000 times less energy consumption than a classical computer. And the second and probably bigger area is all the discoveries that quantum technologies will allow. So not just in terms of energy efficiency, but more generally in terms of resource efficiency and greenhouse gases emissions. So for example, improved models, better predictions and improved mitigation plans to deal with climate change, or greener technologies such as better and more efficient solar panels, better batteries, or more efficient ways to produce fertilizers and for example, optimization of transportation. But this is only the beginning of a long journey, not only on quantum computing, but as you know, we are also working in other areas, such as communications and quantum sensing, so quantum communication and quantum sensing. So we need to increase our efforts to move, as I said before, from lab to market to be able to achieve the full potential of these technologies. With this, I finish. Thank you very much, and we will proceed now with the presentation of our invited experts. And we will be open for questions at the end. Thank you very much. So
Thank you. Yes. Thank you, Oscar, indeed. Having next with us is Valentin.
Hello, good morning, everyone. I'm very pleased to talk about what we are doing in Luxembourg in LuxProvide and with the Meluxina supercomputer. I will start sharing my slides now. So we are extremely proud to present to you what we have been doing over the past years. LuxProvide and Meluxina are part of the greater European effort to bring new facilities to life, and not only facilities, but skills as well. And the focus on skills cannot be overemphasized, in the sense of you are building these nice machines and these very powerful machines that also require a lot of power, but you need to be able to use them. And then you need skills and you need software that are all coming into play to take advantage of them. So in Luxembourg, LuxProvide was created as the High Performance Computing Center and the hosting entity for a European machine named Meluxina. And we have been building over the past years both the machine and the deployment of the main system, but also the teams that are taking care of it, both from the operational side and from the professional services side, to help users take advantage of it. All of it is coming into the national and the greater European context of bringing excellence in research, in science, in innovation, and bringing industry along this journey. So bringing greater maturity across a variety of domains and empowering the digital ecosystem everywhere. And this does not happen only with pure HPC, but also data analytics, high performance data analytics, and AI are very important as well. So Meluxina was one of the first machines to become operational in the European digital decade. We are a Petascale system, so a middle range machine, a quite powerful middle range machine, around 18 petaflops peak aggregated performance, while being ranked as due to the high accelerated capacity on GPU accelerated elements. We are not only operating this kind of infrastructure, but we are also a member of the EuroCC project, where together with the two national partners, University of Luxembourg and Lux Innovation, we are a part of this mission to democratize HPC, so increase adoption of HPC, and in particular for SMEs and startups through multiple programs, including a Fit for Start initiative, which is an innovation accelerator in Luxembourg. So you all came to see what Meluxina is doing. So I'm pleased to start with to show you what the Meluxina was, how it was deployed and the kind of facilities that are behind. So the presentation today is also about sustainability. So I'm very happy to say that Meluxina has been hosted from ground up and built up and hosted in a facility which is uptime tier 4 and ISO 27001 security certified. It's been powered with a 100% green energy from renewable sources, and it's been cooled through an innovative concept that is using biomass recycling from a cogeneration plant that is fueled by waste wood. And this cooling is driving the cooling that goes into the main supercomputer part. And the facility is just next door to the main data center. And the data center itself has been well ranked, and was the winner of the EU Code of Conduct for Energy Efficiency already some years ago in 2018. So the facility already existed. It was not purpose-built for HPC, but was already an excellent green facility. And the Meluxina supercomputer was very nicely implemented inside. And my next slide is about that, to give you a hint of what it looks like to build up such a supercomputer. So it's a Bulsequana machine from Atos, and which is driven by software also from the Partech Competence Center in Germany. The machine counts with something around 800 computer nodes with different capabilities, accelerated and non-accelerated, a large data storage infrastructure, and a high-speed internal network and excellent external connectivity as well. And what you will see in the bottom picture is actually one of the boards that are accelerated boards with 2 CPUs and 4 GPUs that are providing the bulk computing power of the system. And you will see the kind of cooling units that they have on top, and those are used for the liquid cooling part of the system. The machine arrived 1 year ago in 2021, and if you come to visit us today, you will go through this corridor where you will see exactly this image with presenting the front end of the system, which is bringing back also the look from an iconography from Luxembourg, the city skyline, and the Meluxina mermaid, which is a foundation myth for Luxembourg City. From the back, you see also the parts that are more traditional air-cooled units, which comprise the systems powering the workload manager, the network connectivity, and the data platform behind, which cannot be is not such a big user of power, so it's very well efficiently cooled by with air. The machine was built up from ground up to serve a really wide variety of needs, being also the first national supercomputer for Luxembourg, and supposed to take in a wide variety of sectors and domains. Smart mobility, financial services, logistics, space, industry 4.0 are really key sectors for Luxembourg. And if you couple all of them together, you see that you don't do just traditional HPC modeling and simulation, but also data-driven workloads, big data analytics, where when you bring them to a supercomputer become high-performance data analytics, and also AI in the loop of HPC, which really over the past 4 years, 5 years, has provided really a renewed emergence or resurgence of possibilities, a breath of fresh air, if you will, for HPC, as you can now do accelerated computing and doing prediction that was not providing you a speed up for your application that could not have been imagined before. So the Meluxina architecture was designed with this concept in mind. So it's based on a modular design. So there are parts that are modules, computational and data modules closely coupled together in a unique network and piloted with a single unified software ecosystem, both on the operational side and the software stack that is providing applications to users. The main parts, computational parts, are of course GPU accelerated and also CPU based. So the 800 nodes are accelerated or non-accelerated, but being all together coupled in a unified network. And they are linked to high-end storage. So for the data platform, we took the same kind of approach as for the computing part. So there are parts that are accelerated that provide a lot of bandwidth and IOPS. That is allowing you to explore large data sets or do very intensive data operations, while also providing capacity tiers and also data redundancy with backup and longer-term storage, with storage that is also hosted in another of the LuxConnect data centers in Luxembourg, which is geographically separated for redundancy. We put also as part of the machine not only heavy-duty HPC and accelerated and non-accelerated parts, but also elements that are providing some specialized partitions. So in practice, we have an FPGA partition that we are still seeing what kind of users will take advantage of it, which is quite a nice element that is quite unique in the Euro HPC systems. And also large memory module for in-memory workloads that is will provide people with the capability to do data analytics or to work with applications that use large data sets but are not yet HPC ready. So, and then they will still find a way to bring their work in a supercomputer environment, and then they will be able to parallelize and work on accelerating these workloads and applications on the other parts, which are the heavy-duty HPC sections. I think the word of hyperconnectivity was brought up in these presentations just before me. We are extremely well connected to the European network GEANT through the Restena National Research Education Network Provider. But we also have excellent connectivity with public internet and with the commercial internet exchange backbone LUKIX. And there's possibilities from people that want dedicated private links to connect to the supercomputer for data sets that cannot travel through public internet. There's capabilities in the system to do that as well. And the last but truly not least, we have a cloud module as part of the Meluxina system, which is meant not to run core computation, but which is meant to host workloads that you cannot host on pure HPC in a pure HPC context. And that means databases, APIs, user portals, workflow and orchestration tools where you need persistent services that cross what you can do in a computational job. And these are things that we are going to see much more use over the coming years, and it's components of the system where we expect to see much more growth over the coming years. All in all, for you to get a feeling for what it means to have such a supercomputer, we are hosting over 1,600 CPU high-end processors, 90,000 CPU cores. There's 800 HPC accelerators, which have millions of computational cores, and also AI-oriented cores that are very fast at performing specialized work. The system has a lot of memory, and this is needed to be able to run large experiments, and all that is coupled also with high-end storage plus long-term storage, and all together linked into a very efficient and extendable internal network. All of it piloted with the software that is able to take advantage of the variety of computing units that are inside the system. To all together, put everything together, 1 year ago in June 2021, we were ranked as the first in the EU in terms of efficiency of the supercomputer for the GPU accelerated module of Meluxina. We were 14th in the world at the time, and in pure performance, we were 10th in the European Union, 36th in the world. We also ranked the machine across other kind of metrics, just to show that the system has been really designed to be able to do a lot of different kind of workloads. So at world scale, it came up quite high in different kind of rankings that are showing the breadth of capabilities the system has. So I would like to spend a few minutes on software. We are providing users with a software environment that is quite rich, which goes starting with the absolute basics for HPC. It comes from compilers, performance tools, programming languages, but then for things that are really specialized for supercomputers, which are parallelization suites, MPI libraries, acceleration libraries, and then coupled with things that you need for science and innovation, which is libraries that allow you to open a variety of data formats for acceleration of different kind of codes for visualization. And these are the essential building blocks for the high-end frameworks that are being used on the machine. For example, for machine learning, deep learning, and AI. And those are really names that you will hear a lot in the future for that are starting to be applied not only in pure research but also in real applications that the users are doing across science and industry as well. And then in the end, some people want just to bring their data and to run computation, and we are enabling users to do that by providing end user applications that have been built up on the machine and that are taking advantage of the CPU architecture and the GPU units that are part of the system. And they comprise a variety of fields, but molecular dynamics, fluid dynamics are things that are quite often found as use cases for supercomputers, and we're already enabling users to do that immediately the day one they are coming on the machine. This kind of software stack we were providing to all users of the platform. However, we're allowing users to build up their own tooling and to bring their workflow on the system in an easy way through containers. And software containers are something that, well, industry has been doing for quite some time. In HPC, you need to do some specific things to be secure. So there are specific HPC-oriented container systems that are working also with the popular image formats for containers, and this is something that users can start doing on Meluxina day one as well. Applications. So this is more application domains rather than software. So to give you a feeling for the variety of work that has happened already with Meluxina, from the very beginning of the system, from the pilots program, we saw work that spanned really a variety of fields, and all of them have to do with practical applications in the end. So if we take the automotive sector, the goals of work in this domain are coming to improve fuel economy, which is today quite an important target, but also safety. For example, by improving the design of tires and the materials that go into the tires. But automotive is just one sector. For space and space, you can do a variety of workloads from the space domain, from designing next generation engines to optimizing performance of communications, to things like agriculture, where the amount of rain that you're getting on a yearly basis is changing. With climate change, it's quite an important subject nowadays. Yeah, 1 year ago in Luxembourg, we had some nice floods. This year we had some nice drought, and this is changing, of course, how agriculture is behaving. So for agriculture, you need to be able to forecast the yields. You need to understand where water is going to be able to do food planning and to improve food security. AI workloads are also starting to be quite common for HPC. So a lot of research, pure research, is going into improving the AI field itself, while in other cases it's really applied to specific problems. For example, when you're talking with an assistant, be it Siri or the Android Google assistant, sometimes you may work in a multilingual context, and then being able to translate this is quite complex problem. And this automatic speech recognition models today are starting to be improved by working on the algorithms, on the data sets that are the core of being able to interpret speech in a really when multiple languages are exchanged in the same sentence or by multiple people speaking together. Natural disasters are quite important. So detecting floods and doing better water management is quite a classical HPC topic already. The climate neutrality element is also extremely important. The better use of biomass and design of facilities or improving existing facilities that produce heat or electricity from renewable sources. This happens with a lot of computation, simulation, modeling, and digital twins of facilities, of existing facilities, and that's a really perfect work for supercomputers. Personalized medicine can also not be cannot be overemphasized. Building data sets, for example, for applications in drug design and coupling AI machine learning to enhance traditional simulations is something that is happening on a daily basis today. If we look back at the past months, so all the projects that are running on Meluxina in the past year, we see a variety of projects. We have been running 33 projects from investigators all across Europe and the countries that have access to Horizon 2020 funding. And we are going to see a true ramp up, I imagine, in the coming years as more digital transformation is happening across Europe, and more the use of these new machines is being adopted in a variety of fields. Now we have from the EuroHPC projects mostly 9 domains that are getting accelerated by the supercomputer. But I really want to focus that 40%, and this was quite interesting thing for us to see as well. The domain that is the projects are categorized most often is mathematics and computer sciences, and actually that's AI behind it. So it's AI applied to finance, it's AI applied to engineering simulations, and it's AI improving AI itself. So that's kind of a paradigm shift in the kind of workloads that are coming to the supercomputers, and it's something that system operators, supercomputing facilities have been preparing for a while, but it's nice to see today that this adoption is truly increasing. One of the highlighted projects, and it's a flagship project for Europe, is Destination Earth, or Destiny for short. In particular, for Meluxina, we are very pleased to see that this project had an interest in the system, and it's been running from earlier this year. The work there is done by the European Center for Medium Range Weather Forecast, ECMWF, and their core work as part of the Destination Earth project is the digital twins part, and then this has true impact across society and economy. And doing digital twins, doing better resolution projects, higher resolution projects and simulation that could not have been done before on the existing platforms are now starting to take advantage of the new generation of supercomputers and that are present in Europe. And we are extremely proud to be one of the machines that is hosting this kind of project. So I gave you just a sneak peek behind the Meluxina Mermaid and the Meluxina Mermaid and the Meluxina supercomputer. I'm very happy now to see some of your questions, knowing that we have a bit of time until the break that was foreseen, I think, at 11. So I hand over back to the organizers for the Q&A part.
Hello. Do you want me, Alexandro? I go through the questions.
Yes,
Yes.
that would be
Okay.
great.
Okay, thank you. So I will go. Thank you, Valentin, for the presentation. So I will select a few because I see that we have quite a few questions. I will select a few that I saw that it's mainly for regarding your presentation. So the first one will say that it's speaking of skills, how hard or easy it is to find people to work on HPC at Lux Provide.
Okay, it's an excellent question because it has a very good answer. It's really easy for me to say that it's hard. It's hard. So it's hard in the sense of there is a pressure on the market, of course. We were extremely lucky to be able to attract top world talent to join our teams. But we did all of our hiring under COVID-19 constraints. So most of the team started to be hired in 2020 and 2021. at the same time as the supercomputer was built up. We see we hired people with 20 years of experience in HPC, working both in across HPC centers, industry, and with practical hands-on knowledge to be able to maintain a supercomputer and also to provide expertise on top of it. So it was really hard, but I'm really proud to what we have been able to achieve over the past years. And we still have open positions. So if you know somebody interesting that could be interested to join our team, please do not hesitate to reshare our open positions. We are looking across, and have been looking across a variety of expert types. So both from pure HPC domain, from infrastructure, from knowledge into parallelizing and scaling and accelerating applications, and also experts that are experts more in the cloud domain, and the idea of making Meluxina a truly cloud-enabled supercomputer. And those are also skills that are complementary to pure HPC, and running sort of modern platforms for next generation applications will, I think, break the way HPC has been doing things before. So all supercomputers have Slurm or workload manager, and many people run containers inside, but running a full supercomputer as a Kubernetes platform, that's something that needs to be explored. And those are not traditional HPC skills. Those are more cloud HPC skills. So we hope to bridge HPC and cloud with some of the work that we're doing, but we also needed to hire pure HPC experts, without which a supercomputer will not be a supercomputer, and a supercomputing center would not be a supercomputing center.
Okay, thank you very much, Valentin. Another question that we have for you, it's basically you mentioned working with SMEs, but basically the person who's asking the question said, I don't really understand the business model on this one. So how companies actually end up working with you, with Meluxina?
So there's three things that I can really highlight. So first of all, we have a team which is a supercomputing and data solutions team, and they are engaging very deeply within the Luxembourg ecosystem, but also abroad, to see what kind of needs there are, and to bring HPC in the loop of what they're doing today. So they started to engage on the priority domains within the Luxembourg ecosystem. So going for companies that were purely industry, and that they were doing Industry 4.0 work, and seeing the kind of needs they have in terms of pure computation, of simulation, modeling, and data analytics. And they're engaging with them in a prospective way. So seeing what they're doing today, and seeing where we can help them. And this is work that we're doing also as part of a national initiative, which is called Fit for Start. And the Fit for Start initiative last year, it was already the 12th edition of this program, had an HPC and data analytics track. And as part of this program, it was geared to startups more than SMEs. The idea was that we were part of the mentoring program, bringing a bit of knowledge to startups, so to high potential startups that could use supercomputers. And they were doing, for example, flooding analysis, and also know your customer work, which was more data analytics rather than pure HPC. So the teams provided them with a bit of knowledge, how to work with a supercomputer, what you can do with a supercomputer, while also getting access to the infrastructure to work. So we are also in charge at the national level in the EuroCC National Competence Center of the business development and interaction with industry parts. And there we are, again, as part of this mission, we are doing presentations to various industries from large to small, and guiding them or providing them the first hint of what they will be able to achieve with supercomputing.
Okay, thank you very much, Valentin. And also, I think there are two questions that are related to the use of specialized hardware. That it's one is basically is does Meluxina and other Euro HPC infra have installed custom design hardware, or only brand systems, and also if there is any FPGA or ASIC hardware accelerators available at your HPC. I know that Meluxina has FPGAs, so probably if you want to take these two questions.
Okay, thank you very much. So we do not have truly custom, well, all supercomputers are custom in the sense of the kind of specialized infrastructure that they run. But we are not running any specific custom-made CPUs or GPUs. Most of the computational power comes from high-end HPC and AI components, so CPUs, AMD EPYC CPUs and NVIDIA A100 GPUs. Of course, as a supercomputing center, you buy them at a scale where you're not able to have this kind of machine in-house. So the sizing of the system is really what makes a supercomputer. It's not, we do not need to run extremely specialized units, but these are units that are available in the market. The FPGA part is maybe the most specialized part of the machine. The FPGA components themselves, the ones that we chose for the machine, are Intel Stratix 10 MX units, and they come with a lot of onboard memory that you are able to use for HPC applications and data analytics applications, but they would be the most exotic component in the system. And to my knowledge, they're still unique in the current generation of Euro HPC machines out of the 8 sites that were originally slated to install systems.
Thank you, Valentin. And we'll go with the last question. So I know that there are more questions, and I'm keeping a few of them for the other participants. So it's basically, so the question is which industries are the keenest to adopt HPC and why?
We see a lot of interest from the space domain, and space is a big favorite for Luxembourg in particular. For the space domain, of course, there's the parts of materials design for next generation satellites, but also for doing space weather forecast, which is weather forecast but applied to space. And as you well know, you have a lot of elements that are orbiting the Earth, and you need to, if you need to send a new satellite or a rocket there, you must make sure that it's going to survive. And this is quite complex dynamics environment. So space weather forecast is actually an important part that I hope we will see more in running on Meluxina over the coming years. And also the field on agriculture, I would hope, is going to be a big user of HPC, and knowing that by taking images from space, coupling them with sensors that are ground-based, you are able to do a lot of forecast for how the food yields are happening, what are the crops doing, what's the quality, and across space, across agriculture, or also industry, manufacturing industry, there's a lot of potential for HPC. For manufacturing industry in particular, there's Industry 4.0, which is quite well established over the past decade as a user of digital user of HPC, maybe not really, but doing digital transformation across a variety of companies. In Industry 4.0, now is transitioning to an Industry 5.0, which is bringing human in the loop, which is aided by AI, for example, to see when there's problems in the production line, or to ensure the quality of things while maintaining people as decision makers. And these domains, I would believe, are ones that are really going to grow over the coming years, and in users of becoming users of HPC. The software tooling for them is going to be very tricky, because they're used to kind of tooling that is maybe not well adapted to HPC, or not yet. And although we sometimes joke that that software is something that moves beyond the speed of light, is the only thing that moves beyond the speed of light, software is not yet taking advantage of even the current generation hardware. So you're always going to be able to improve what software is doing on top of existing machines. But this software needs to be adapted to what industry needs. And then it took, for some scientific domains, 40 years to come to software that is that is well tested, well and efficient, and which needs to continuously be adapted to new machines, while the software that is being used in many industries is perhaps not at this level already. So I foresee a lot of work from application specialists and domain specialists working together to bring industry workloads to supercomputers. Well, the driving factor is the need of industry to be more agile, to do better products, to do virtual testing, while the software is not yet there, so it needs to be adapted and accelerated and parallelized.
Okay, thank you very much, Valentin. Thank you for the presentation. We will continue with because I know that there are more questions. We will continue with other questions later with both Pekka and Christel for HPC and for Quantum. And I pass it now to Alexandru for the break.
Yes, so thank you again, Valentin, for being here. It was quite experience, and we really hope you find the good people that you are looking for, or because it's quite complex, and we know how hard it is in really complex businesses to find the right people. On a session yesterday, we also had one company, and they mentioned that they were also looking for around 300 people. So yes, it's quite hard. But thank you again for your contribution. So we still have a bit to go, and I think we are gathering the insights, and we can see from your questions that indeed the session, although technical and very, let's say, limited enough for everyone, we can see that we are in need of such sessions, because we do need to figure out the best way to go forward and what are the most important things. And also, let's say, to bring more focus into HPC and quantum, as definitely it will be part of our future. Now, continuing with us, we have Dr. Pekka Manninen. Pekka, the floor is yours.
Thank you, and good morning also on my behalf. And I was asked to give a briefing about where Europe and Euro HPC is going with the pre-exascale systems. And this is one of the 3 ongoing pre-exascale installations in Finland. And I've been in charge of the this initiative basically from the beginning, and keep on doing that while we are running to the operation state. As a difference to the Meluxina, LUMI is a joint effort by many European countries. So here we see 10 countries that form the LUMI consortium, and together with the Euro HPC joint undertaking, we are investing, as well as then in a good collaboration governing and operating the LUMI supercomputer located here in northern Finland. And with an idea that then per the investments to the total cost of ownership of the system, the system resources are being then shared in accordance. So European Union distributing 1/2 of the LUMI resources, and the 1/2 then by the consortium countries, as basically they see best. And second, on top of the consortium, let's start from the question. So why did the European Commission decide to locate the system in Kajaani? Our belief on another big is that this is a combination of the consortium. So it is a consortium of lots of competence and established tradition in HPC, and then the Commission was convinced that we are capable of supporting the users and bringing the users there and operating the system. And the other factor to the decision, I believe, was the site. So LUMI is located on a former paper mill in Kajaani, with the paper production gone to Latin America somewhere in the early noughties. But the site remains, So we, CSC, which is the National Supercomputing Center in Finland, have been running our systems there for 10 years or so, and I wanted to offer this location for the pan-European supercomputer as well. And when we started looking at the site for LUMI, there was just like a very big empty hall, the paper machine being demolished from there, and we ended up building this kind of a building within a building. So this is our data center. It looks like a snowbank because LUMI means snow in Finnish and in Estonian. So it looks like a pile of snow. So it's a two-story building with the upper story hosting the system, the white space, and we have the basically one full floor of like a raised floor there, and all the like cooling and electricity systems are being in fact on the one floor below this hall. But in addition to the floor space, the very key factor here is that we have an abundance of clean energy in northern Finland. So LUMI can, with 8 megawatt power consumption, it's a small deal as compared to paper machines. So the electricity comes into the factory area from 3 main grid lines and capable of hosting over 200 megawatts of energy demand on the very same site. And for this is a very reliable. So there are virtually no blackouts or any issues on the electricity on the site. And due to the location up north, so we can do free cooling around the year. So we can just let the excess heat out if we want to, and this renders the power usage efficiency into record-breaking values. But in fact, we are not letting the heat to go to waste, but we are using it in the district heating system of the surrounding city of Kajaani. So the heating, well, in Finland we need to heat up our houses quite many months per year, and it's typically done in this kind of centralized heating factories, and then the hot water is being circulated through the city, so like thousands or tens of thousands of apartments. So the local heat factory happens to be 200 meters from LUMI, so it was pretty no-brainer of building a pipe to that factory and then use the excess heat of the system in the city heating. So in fact, 20% of the city is being heated up by LUMI supercomputer. So somebody's waste is somebody's treasure in a way. Kajaani may be a bit remote, but it's part of a very strong internet connection, so we can demonstrate easily hundreds of gigabits per second transfer rates to Kajaani site, and also as a robust site, we can live with very high up security standards. But what we have then achieved over the course of years is supercomputer that at the moment is the 3rd fastest in the world and the fastest in Europe. So it is one single contract from Hewlett-Packard Enterprise, and that they sold us a system under the Cray EX brand. So we listed the partial system, so only less than 1/2 of the GPU nodes were enlisted, but it still received the number 3 spot. And as already referred to, it's already number 3 on the Green 500, which is the energy efficient list, where the 2 top spots are by exactly the same architecture in the US. But we've been also claiming that it's perhaps it's maybe number 3 there, but it should be number 1 if you take into consideration that LUMI is being run with 100% like carbon neutral energy, whereas the US systems are not. So in our opinion, we are the number 1 in what comes to green supercomputing. So LUMI is committed to achieve 375 petaflop in high-performance Lindbergh benchmark. It's 550 petaflops peak performance for the GPU partition, and with the sustained performance figure of this, which is roughly equivalent to a bit below 2 million modern laptops. But we can fit it in this kind of compact space of perhaps 2 tennis courts. So it's not any bigger than that at the end of the day. But more importantly than the peak performance or the benchmarking performance is that what we think we have achieved is a very modern platform for high performance computing, AI, and data analytics workflows of today and this decade, and hopefully also the convergence. What comes to the system design and the what we want to achieve really with this system is of course top-notch science. So we want to see scientific breakthroughs of like a very high value for advancement of science and human the society in general. And when the Euro HPC expression of interest came out, what we had the system design in mind was this kind of a Swiss Army knife where you would like a pull up some kind of a knife or corkscrew for pretty much anything that the science in this decade are needing for their computational platforms. And of course we had some kind of driver cases in mind. So, but this is of course not everything that the system is going to do. But we want to position the system, especially in terms of climate research, especially and now it's becoming very topical with the Destination Earth initiative and being a one of the leading platforms or the key platforms for enabling Destination Earth. Also, data science and machine learning, artificial intelligence is obviously one of the key drivers. But also more traditional simulations what comes to space weather or fusion power or different kind of plasma simulations. Life science in terms of biophysics and bioinformatics and so on. Material science, the very traditional use of HPC. But also emerging communities, supporting emerging communities like that of in humanities and social sciences. And in fact, the natural language processing is one of the most kind of biggest domains in the system in the GPU piloting phase. But also a different kind of like a large scale data analytics cases occurring in social sciences. Also, LUMI as this kind of like a major platform, we need to be ready for supporting governance and public sector, and therefore be ready to host urgent computing needs if in a crisis situation, be it related to new pandemic outbreak or something to the national security. For more tech-savvy audience, so what does this mean in terms of numbers, or what is a supercomputer? So LUMI is in a sense, there's a very much similarities between Meluxina that Valentin was going through and LUMI independently, but this is, I guess this is a kind of like a, from the same design philosophy, we end up in the pretty similar solutions. So also LUMI has this kind of several partitions integrated together. Well, seamlessly integrated together, and this partition are the GPU partition for the number crunching power, supplementary sort of traditional CPU processors. In case both are like these are all AMD systems, so AMD GPUs and AMD CPUs, and this kind of a spice is like different separate data analytics partition place for running microservices. We have also quantum computers or quantum processors integrated to the system, so people can do have the first steps in quantum computing from LUMI, and everything is supported by an storage subsystem based on well this kind of very fast flash memory storage, more traditional parallel file systems, and object storage. In terms of timeline, the LUMI procurement was completed at the same time with the two other pre-exascale systems in Italy and Spain, so that we were announcing the contract, or the JU was announcing the contract in the fall of 2020, October, to be more precise. And of course, the system construction started immediately after the signing of the contract. We were ready with our Snowpack data center in March 21, and the first cabinets of the system came in June 21, and we were able to open the first phase, which is the everything else besides the GPU partition. We were able to open it in last year, October, so roughly 1 year ago, for the first customer cases. And the general availability, or it was the first phase, was on everybody's use since the beginning of this year. And now in 22, we've been building the GPU partition, the kind of a main thing there, so that we had the 500 listing, and we have now enrolling we have had a pilot users in since the late July in the system. And now we are reaching towards the general availability of the system, targeting the system acceptance now, hopefully within the 1 month or something from now. And then LUMI is finally ready and ready to serve European science, European R&D in SMEs, as well as the different research institutions. We are not going to hit the #1 spot in the 500. That's reserved for US frontier system. That is going to be the king of the hill for quite some time. But where we want to be the #1 is a user experience. So we've been working on several teams along the road while building the system. So for instance, we want to ease the use, enhance the ease of usage of the LUMI resources by providing this kind of a high-level interfaces to the computing resources, like akin to Jupyter notebooks and RStudio and so on. Similar to Meluxina, we have a pretty rich stack of software tools and pre-installed software, also, and not only software but also like a reference datasets and also this kind of different data repositories close to the system are being built. And also we've been finding ways how we can convince the industrial usage to the system via having a more elevated security levels to the system, and also be able to comply with the different criteria for handling person data on the system, or sensitive data. But basically this is what we think LUMI provides for us, this kind of a capacities for scientific research. Of course, the first and foremost is this extreme computing capability. So one can do simulations on a fidelity on the time or resolution that hasn't been possible ever before. However, LUMI is not only for this kind of very big, meant for only for very big GPU-based simulations or AI training runs, but it also welcomes mid-range or even this kind of like a single core computations, if it's just like if you can provide a value add for this research team. And one can combine different resources within the same workflow. So if you recall the snowflake picture there, so from different partitions, so mixing and matching GPU resources, CPU resources, to the same workflow, even the same binary can harness them. They are in part of the same network topology very seamlessly. Also, I think the interactive partition is pretty kind of like a beefy. So I don't think I'm not aware of very many of similar like a level partitions for like a data science. We do think that the work on the data repositories and the software can be an asset of its own. Also, the ways of like dynamically handling data and data streams. So streaming data in and out from the system and syncing with different kind of external observational or other data repositories and data spaces. And of course, this federation of data and access, what your HPC joint undertaking is working on, is a very important topic, and we of course want to be there for kind of like supporting that effort. And then, of course, we want to expose our users also to the emerging technologies like quantum computer via the LUMI environment. So this is what I had in mind for today. So please follow our progress via the LUMI supercomputer.eu website. There are different kind of like articles and user where do people use this or intend to use LUMI system, and there's of course some social media presence. And yeah, I think I stop here and see if there's interest for any quick questions, and I'll be around also towards the end of this session for any further questions. So thank you for your attention and also for inviting me to this session.
Thank you very much, Pekka, for the very interesting presentation. We have a few questions, so I see that some of them can be more linked to what you have presented, and some of them are more for ourselves, for the Commission. So the first one is if you could provide a brief overview of the cooling system. So you have talked a little bit about how it works, but maybe you can go a little bit more in detail.
So LUMI is most of LUMI, so the compute cabinet, so the CPU partition, GPU partition, so basically where the most of the power goes in, is directly liquid cooled system. So it is a more or less room neutral. So the warm, we operate it as a kind of as warm water as we can. So the water goes through the basically component level on the compute page, comes out of course like a water, and then we prime that heat to and feed it to the district heating network. Of course, we can do the free cooling or combination of it, so we can put half of the heat to the district heating and half to the outside air, or slide somewhere in between. But that's basically the main thing is this directly liquid cooling of the system, and then the storage and other systems are air cooled systems. Like there's like a very standard IT racks using air cooling.
Okay. Thank you very much. And we have another question also that it's basically the person who is asking the question is basically saying that you have seen or is asking if you have seen an increase in the appetite for artificial intelligence and data analytics in the last 2 years, and also do you see anything changing in the future in that area?
Sounds like the who asked the question already knows the answer, but yes, of course we have, and it's visible on the projects allocated to LUMI, the pilot projects that we're applying for LUMI access and so on, and there are many. Yeah, I think we need to somehow some part of that rethink the classification here. So because this something that this like a coined as AI, they come from many different domains. So they may relate to natural language processing, or they may relate to just like doing reanalysis of some simulated data sets, or it's so basically it's present on very many scientific disciplines. just like there's a many low-hanging fruits at the moment. So there's so many things that we can do with the methods coming from the AI community to the as applied to the scientific fields. So yes, I mean, we are in a data-driven science era and it's of course visible from everything we do on LUMI, or we, well, not we, but the end user and the scientists do on LUMI.
Okay, thank you. We have thank you very much, Pekka. We have another question, but I think this is more for our colleague Juan. That is basically, what is the role of open hardware in the HPC ecosystem, and do you support any research and infrastructure in development of RISC-V based accelerators? So I don't know, Juan, if you want to take it.
That's a good question. So indeed, OpenRISC-V is an emerging technology that is very promising. It's flexible. It's open source, so there's no need to pay license fees. So to a certain extent, it's very promising. The KDTJU, so there's a Key Digital Technologies Joint Undertaking, has recently released a report on the opportunities that RISC-V may offer Europe in order to gain digital sovereignty. In this report, the area of advanced computing and HPC is signaled. So from our perspective, we are exploring possible activities with OpenRISC-V. This will be discussed in the coming days in the context of the JU and elsewhere. So indeed, we will look into this promising. I think it can be very positive for Europe, but again, we need the mobilization of stakeholders, of countries, different supercomputing centers. So we're exploring it very, very thoroughly. And indeed, yes, we're going to look deep into that. And we believe there's an avenue important avenue for opportunity for Europe. And this will be materialized in the coming months, let's put it that way.
Thank you very much, Juan. We have another question for LUMI, and it's basically about the LUMI consortium. So the person who is asking basically is saying that you have mentioned, Pekka, you have mentioned the LUMI consortium, and they are asking is what it's bringing together the unique expertise and experience of each country, and if you can provide some examples of that.
So, like I said, this is an first time in Europe where the European countries do jointly invest so much in high-performance computing, and so we are like I think it's first, but definitely not the last time where we can really find like a way of doing over across the boundaries collaboration. So we are learning a lot on the kind of a political level, but on the technical / operational level. What is kind of a new thing is that the user support is not provided by CSC only, but it is the team is distributed over the consortium countries. So there is a virtual team closely working together and as like one organization, but they are located on these different HPC centers across the continent, and with the idea that they are still working for their home institutions, so they always can go to the coffee rooms and the seminars and whatnot on their home organizations, and they can then bring this competence to the LUMI user support team network and to the good of the whole user base. So we can basically pool and share competencies from 10 countries instead of trying to establish all these needed skill sets to being based in Helsinki. And also this is one way of tackling the recruitment problem of finding the competencies and then the competence problem, because we don't need to convince people to come to the Helsinki, which is not known for its friendly weather or good food or anything like this. So it's a way of doing this kind of a European-wide competence development and competence pooling.
Okay, thank you very much, Pekka. I have a last question. I think it's also probably for you and also for Juan. It's how basically, if you are a researcher, what do you need to do in order to use the supercomputer facilities? So normally, how it works. So I don't know, Pekka, if you want to, from your side.
Pekka, would you like to explain what's an access call and how this is arranged in LUMI?
So, well, I can take it if so we have like a I mean, I don't know. I hope not stepping on his toes here, but the Euro HPC, how it works is that there's like a single like a centralized set of calls for all the Euro HPC systems. Now the 3 pre-exascale systems, the 5 Petascale, also the upcoming exascale and the mid-range systems and so on. So they are all coordinated by so everybody affiliated to a European institutes of these 33 countries can apply from these calls. And you can target some of those systems for your project. And also the project can be like a transfer between the machines if there's no room and it would suit better in another machine. So that's we have this pan-European allocation mechanism for the commission share of the systems. And in addition, there's half of these pre-exascale systems are then on the national hands. So like I said, so we do it on the consortium country level. The Italian system will do it in Italy, and then the Spanish system will do it in Spain. So kind of like a two access routes. And for LUMI supercomputer, for instance, if you go to our webpage lumisupercomputer.eu, there's the Get Started page where you can see how should you do it if you are either in a consortium country or some other country in Europe. So how to get an account and an allocation on the system.
If I may add, for the European time, I think I would address the researcher or the groups, the labs to the HPC JU, whether they could find information on how they can gain access, at least make a bid to be granted access to any of the European supercomputers. So that, as Pekka signaled, half of the access time belongs to the EU and is managed by the JU, the HPC JU, and the 50% remains within the context of the national time, and the rules and approaches are dictated by the national systems, the hosting entities. Thank you.
Thank you very much. So with this, we will finish the part that is related to HPC. Thank you very much, Pekka, for your time. It was extremely nice in the presentation. Anyhow, you have for everybody that is listening us or is watching us, you can still do questions, and Pekka will still with us until the end. We will move now into the quantum world. So we'll go into one of the projects that we are currently doing as part also the European Commission and the Euro HPC. And for that, we will have the Professor Dr. Christel Michelsen. I think you are connected, so please go ahead. Thank you very much.
Yeah, thank you very much, Oscar, for the introduction, and thank you very much for having me here to give already an introduction to the project HPCQS, which stands for High Performance Computer and Quantum Simulator Hybrid. And this is indeed about integrating quantum computing devices in the HPC infrastructure. So, yeah, for a long time, already for quite some time in Jülich, in the Jülich Supercomputing Center, we had the vision that high performance and quantum computers have to be linked. And they have to be linked for several reasons. Obvious reason is that we use these HPC systems to emulate or simulate these quantum computing devices. And they can be of any type, digital or analog quantum computers, meaning gate-based systems or simulators or quantum annealers. So if we simulate them or emulate them, we can use our HPC system as a benchmarking tool for these quantum computing devices. And this helps us not only to see how they perform and things like that, but also understand how they operate. And if we understand how they operate, we can also see where they make failures and then try to help in improving the design of these quantum computing devices. But actually linking them, there the ultimate goal is to come to hybrid HPC quantum computing or quantum simulator simulations, and this for real-world applications. And also Europe have given funding, a lot of funding in quantum technologies. So not only in quantum computing, also in sensing and metrology, and also in communication. And in these three fields, the European Commission also had the goal to set up infrastructures. And for the quantum computing and simulation, this infrastructure is called EuroQCS. So the goal in Europe is to set up an infrastructure for big data, artificial intelligence, high-performance computing, among others, but in which these quantum computing devices, computers and simulators are integrated. And this picture was already announced in the SRA of the Flagship in 2020. Now in 2021, Euro HPC gave support for the first hybrid HPC quantum computing infrastructure in Europe. And this is the project HPC QS. Let me first show you some key facts about this project. It's a project that runs for 4 years. It has a total budget of 12 million euros. There are 6 European countries involved, including 15 different partners. So we started on the 1st of December last year. So the project will run until November 30, 2025. Forschungszentrum Jülich is coordinating this. Actually, I'm coordinator of the project HPC QS. And as I mentioned, we have 15 partners plus 3 linked third parties, all coming from 6 different European countries. And here in this circle, you see the partners that are involved. And you can also recognize here that several of the big HPC centers in Europe are also involved. So we have the HPC center in France. This is the one of CEA in Paris. Then we have iCheck in Ireland. We have the Barcelona Supercomputing Center, and we also have Shineka as a partner in this project. And you can also see that these are not only HPC centers that are involved, also research centers and university, and small to big companies. A little bit more about the finances. As I mentioned, we have a total budget of 12 million, and the European contribution, as is the case for these Euro HPC projects, is 6 million euro. So this means that the remaining funding comes from the partnering European countries. So we have 6 different countries: Germany, France, Italy, Ireland, Austria, and Spain. What is going on in this project? And to show you this, or to illustrate this, I show you here the work plan. So as in every project, of course, we have a work package on project management and the scientific coordination. But you see here work package 2. And work package 2, one can see somehow as the heart of the project. This is a work package in which we have run the procurement for the acquisition of 2 quantum simulators, and I will come back later to this. And it's also in this work package that we coordinate the integration of these 2 simulators in 2 HPC centers. One is the one of CEA in Paris, and the other one is the Jülich Supercomputing Center in Jülich, Germany. Then we have a work package that is responsible for the development of the infrastructure software. And we also have another work package that is more responsible for the programming technologies of this hybrid infrastructure, and also for technical libraries to make the life of these hybrid HPC quantum programmers a little bit easier if they want to use this hybrid infrastructure. In a co-design approach, we develop and implement also use cases. So these are pilot demonstrator use cases to find out what one can do with the type of quantum simulator that we have acquired, but also what one can do with this hybrid infrastructure. We will allow for a limited amount of external users towards the end of the project. And in order to do this, we know very well from our HPC experience that it's very important to provide these users with training, support, and all kinds of other services. So this is also something, this training material and these training sessions, which will be organized within this work package 5. And then, of course, we have our other standard work package, which is about dissemination, communication, and exploitation. So, in a nutshell, what is the aim of this project? So, on a high level, we prepare European research, industry, and society for the use and federal operation of quantum computers and quantum simulators. So this is the first project in this kind. So what we do in this project, we will develop, deploy, and coordinate at European level a European federated infrastructure which integrates 2 quantum simulators of the French startup company Petascale. They deliver us quantum simulators with more than 100 qubits, and these qubits are based on the neutral atom technology. One of these systems will be integrated in the HPC infrastructure in the Jülich Supercomputing Center. The other quantum simulator will be integrated in the Joliot-Curie system of CEA in Paris. And this system, or this quantum simulator, is acquired by Janssen. So we have here this linking of HPC and quantum simulators in 2 different HPC centers. Now, these 2 HPC centers will also be federated so that we have one big federated infrastructure for this quantum simulator HPC integrated systems. Now, in the end, the infrastructure will be accessible via the cloud for public and private European users, and this, of course, on a non-commercial basis. On which technical components is our HPC-QS integration based? We have 2 main technical components. The first one is the Atos quantum learning machine, which will provide us with the programming environment. And as many of you might know, this is a system for direct access to quantum computing backends, and the quantum simulator is one example of it. Now, for the integration into the HPC system, we want to have a lowest latency integration. And to be honest, this is a research project, so we will consider a latency that is as low as possible. But we know that this might be for production, it must become much lower. But as I said, the first thing is to integrate, and then we can have a look into how low we can make this latency for the integration. What do we use? We use software which is based on Partix Parastation modular middleware suite. And this is software which has been developed in a series of EU-funded DEEP projects. So this is an ongoing series of European projects for HPC, but this software can also be used to integrate quantum modules, and a quantum simulator is one of these possible modules. So actually this integration is an integration in a modular supercomputer architecture. And I made here a schematic picture of the modular supercomputer architecture at the GSC, where we have a cluster which contains mainly CPUs. We have a booster which mainly contains GPUs. And then we also have storage modules, a data analytics module. And we, for a long time, reserved, so to speak, two more exotic modules, one for neuromorphic computing systems and one for quantum computing devices. So in this project, we will integrate a quantum simulator into this architecture. So this will then be one of the systems in this quantum module. So if we integrate this QPU with more than 100 qubits and its front end, we of course need to integrate it in the full management stack of this modular computer. So we will have to include this into the user and the software management. We also have to see that we have access to the storage and many other things. The low latency connection to other modules. For the hybrid computation, we need access to the CPUs and the GPUs. We will do this via a federated high-speed network. And of course, we also have to then integrate it in the scheduler and also see that we have good management of both HPC and quantum resources, and this at system level. Now, if we have integrated the QPU in our HPC infrastructure, we also have to come with new usage models, because we have simulations which require a tight coupling between the quantum device and the HPC system. And of course, there we need a benefit from an efficient data exchange, even if this is a small amount of data. We can think of workflows, HPC workflows, in which we take some part away from the HPC system and give it to the QPU. So this requires then, of course, also a pre- and post-processing tasks on the GPUs or on the CPUs before the QPU can do his work, or even after, when the QPU has given back his results to the CPU or GPU. So we have to come to a really unified environment. And as I mentioned before, this is really on all levels. So on the levels of software, but also on user level and also storage level. Because we have our users, and we also want to make their life easier if they want to program such a hybrid system, we have foreseen as I already indicated, in the project, a work package that's devoted to the development of technical libraries and tools. So the goal is to translate particular use cases, and in this case, this can only be prototype use cases, into quantum programs for the quantum simulator. And this without the user to have to deal with too many of low-level instructions. We have these libraries. What is also important in this respect is that we also pay attention to the development or the further development of compilers. And here we focus most on variational algorithms. If you have such a system, it's very important that it's benchmarked. So one has to take a look at tools for benchmarking the system and also to do the performance analysis of the system itself. Benchmarking in this particular case also includes cross-platform benchmarking, meaning that we run also the use cases or solve the use cases on other quantum computing devices, but we also solve them with quantum computer emulators and also classical software. And as I mentioned before, we will provide cloud access to this federated infrastructure. How do we do this, or which technology will we use there? For this, we rely on what already has been developed and is in use at the Jülich Unified Infrastructure for Quantum Computing at the Jülich Supercomputing Center. So there we have a quantum computing platform as a service. It's based on Jupyter Hub technology, and we use Unicore for the implementation of the platform as a service. We are thinking and discussing within the project to use a Phoenix-like authentication and authorization infrastructure service. So that at a later stage, maybe this platform can also be integrated in the Phoenix platform. Use case and training. Users are very important, so we will have a co-design of the hardware and the software with particular use cases. So which use cases are we thinking about? First of all, we have, of course, our performance and analysis tools for the quantum simulator. Then some particular simulations in physics, the quantum approximate optimization algorithm for particular optimization problems, VQE, and some basic quantum machine learning. As I mentioned, in one of the work packages, work package 5, we are developing training material, user guides, and courses for, first of all, our internal users, but also for the external users that can make use of this hybrid and federated infrastructure. And this we do for as well scientific and industrial users, which each have their own needs. So, and this was a quote of mine, so this information technology being developed in this project will place Europe at the vanguard of quantum computing, and this one also has to see in the European competition with the United States and China, which was already a topic before in this online session. And I would like to conclude now my presentation with the saying that HPC-QS will be an open and evolutionary infrastructure that aims at expanding in the future by including a diversity of quantum computing platforms. So in the future, we hope to expand that we do not only have integrated a quantum simulator, which is an analog quantum computer, but also gate-based systems. And this at different technology readiness level, and by allowing the integration of other European quantum nodes. So in this respect, we see HPC-QS as a second step towards the Euro QCS infrastructure, which is one of the goals of the European Commission. So thank you very much.
Thank you very much, Christelle, for the interesting presentation and providing more information of the integration between quantum computing and HPC. We have a few questions that some of them are from they have been there for some time, but I was waiting for, because they were more on the quantum computing area. So I will go through the questions. The first one, I think is for Christelle, is basically they are asking which are the most promising technologies in quantum computing.
Yeah, so there we have to make a distinction between the digital quantum computers, which are the gate-based systems. And there, for the moment being, the biggest systems are the systems that are based on the superconducting qubits. We have also several European projects there which are developing these systems. Another technology which is also quite evolved is the one based on ion-trapped qubits. Then we come to analog systems. So of course we have different technologies like qubits based on photons and so on, but these systems are not yet so well evolved in terms of size and in terms of quality. And then we go to the analog systems. So analog systems like the quantum simulator, there we have systems which are based on neutral atoms, like the quantum simulator of Pascal, which, by the way, will also evolve into a digital system. So this will also become a gate-based quantum computer in which one can control all the qubits individually. And then there is, as an analog quantum computer, also the quantum annealer. And there, the biggest system is a commercial system with more than 5,000 qubits. So that's the biggest, I would say, quantum computing device that is currently available. But as I said, all have different types of computing, digital, analog, and different technologies.
Okay, thank you, Christelle. We have another question that basically they're asking if you could describe a little bit more in detail the interface, the hardware interface between the quantum computer and the HPC system. Especially, they are talking about the hardware and if is based on any specific standard.
Yes, so at the moment we cannot speak about standardization in this integration. So there are definitely different ways on how to integrate quantum computing devices in infrastructures. And in my opinion, this should remain the case for quite some time because this is a young technology. So starting with standardization too fast may exclude some opportunities. So this is something which we should not do. Here we will have, in the first place, we try to have a deep integration. So to include this quantum computing device really as a module in a modular HPC infrastructure. Having been said this integration is then entirely based on software. So this module will be integrated by software. And as mentioned before, this will be based on the Parastation Modulo suite, which is already in use for the operation of modular supercomputing architectures. It's an extension.
Okay. Thank you very much, Christelle. I think I'm aware of we are now reaching the end of the session. I have another question. I think it's more for the Commission. Is basically if you could please tell us if there are HPC and quantum technologies task force group in the European Commission. And where you can join for all these type of questions. So there are some expert groups on these topics, also their projects. So we have a coordination and super action that is taking care of all this. For this, what I will recommend is to go to QT, so Quantum Technologies QT. .eu website, and there is a contact. You have almost all the information of what we are doing in the European Commission on quantum technologies, and you have also a contact link, and you can send us an email, and we will reply to all these questions. Also, I saw some questions on cryptography and quantum cryptography or post-quantum cryptography. We don't have time to go through them today, and apologies for that. With this, thank you very much, Christelle, and the rest of the speakers, and I pass it to my colleague, Alexandro.
Thank you, Oscar. And indeed, a big thank you as well for the speakers on my side. And I hope for you, the audience, that you did get insights today, which were, let's say, harder to get in other places. And indeed, as we saw, we need to have our attention on HPC and quantum because it will be part of our future as data is becoming more and more in volume. So we will need to process it more smartly. And not only. We have only, let's say, a day and a half left. Today, we still have our session on industrial platforms, for which we wait you at 2 o'clock. And tomorrow, the session on mobile generations from 1G to 5G, as well as the Commission's closing session, which will put EU digital infrastructure in a more global ecosystem, and we will approach how we can better improve our greening efforts in this area. Thank you very much, and let's see each other after lunch. Thank you.